In this video, we will look at how the different error types propagate into our estimation results. So the question is, how do the errors in the observations y propagate in the estimate x hat? Let's first quickly review the different types of errors and get an idea of their impact on x hat. Here we see the same examples as shown in week 1. Firstly, the random errors. They will result in observations fluctuating around their mean. This is an example where a systematic error corrupted all observations, resulting in the offset between the truth and mean. Finally, an example with 2 outliers is shown on this slide. Let's take the example of the canal width observations. This time we collected 5 independent observations with a laser distance device. The functional and stochastic model are shown here on the right, and the observations are shown in the graph, together with the true width x and the estimated width x hat, which is the best linear unbiased estimate based on the 5 observations. In the presence of only random errors, x hat will not be exactly equal to the true width, since we know that the mean of the errors is 0 only when we take many observations. The more the better. The difference between the estimated x hat and the true x is the estimation error. This error is the result of the random errors propagating into our estimate. Every time we repeat the 5 measurements, the estimation error will be different, since the random errors in the observations will be different as well. This graph shows the estimated widths after many repetitions of the experiment. So each red cross now corresponds to an estimate of the width based on a different set of 5 observations. Similarly as for the observations themselves, the estimates fluctuate around our mean due to the propagated random errors. Indeed, we can see that the mean of x hat equals x, which corresponds to our unbiasedness property. Furthermore, these results show that the dispersion or variance of the random errors translates to a variance of the estimation results. This variance of x hat can now be determined such that we know the precision of x hat. We can estimate the precision of x hat in this case since we repeated the measurement many times to get a large number of estimates, which are then realizations of the estimator x hat. In practice, of course, we don't want to repeat a measurement campaign many times in order to determine the precision of our estimator. Fortunately, we learned that we can also apply the so-called mean and covariance propagation laws to show that our estimator x hat is unbiased and to determine its covariance matrix. Recall that the precision of the observables is described by the covariance matrix, which is equal to the covariance matrix of the random errors. According to the mean propagation law, we found that the best linear unbiased estimator is unbiased, and the precision as described by the covariance matrix of x hat followed from the covariance propagation law. This result shows that the propagation of random errors into our estimation results is captured by the covariance matrix of x hat. Now let's first look briefly at the 2 other types of errors and how they propagate in the estimation results. Systematic biases and outliers are unknown but deterministic parameters. As such, the resulting error in an estimate x hat will be the same every time you repeat your measurements. In the figures you see 2 examples with estimates where each estimate is the blue based on a different set of m observations. The left figure shows the estimates in the presence of only random errors, and on the right you see the estimates with the same random errors plus a systematic bias. In the latter case, the mean of the estimates, as indicated by the red line, is not equal to x, and the corresponding offset is equal to the estimation error due to the systematic bias in the observations. This shows that systematic biases will not influence the precision of the estimator, but only the accuracy. The same applies for outliers. Now, how to check for the presence of systematic biases and outliers, that will be discussed later. This is important since obviously these errors propagate into the estimates and resulting in estimation errors. But first, we will focus on random errors by assessing the precision of the estimator as an important quality measure, and we will also look into the interpretation of the covariance matrix of X hat.